So thank you, Jim, for organizing this session. And it's good to be here amongst people thinking broadly about economic issues. So I'm going to, give a summary. First part of the talk will be an introduction about my thinking of trying to understand the role of energy or perhaps resources more generally in the economy over the long term. And when I say long term, I mean effectively from agrarian to fossil economy or the industrial economy to then help us think about transitioning from a fossil economy to potentially renewable economy, and what are the pieces of an economic model that might be required to do this, or what might be some thinking behind this that might, and some trends that we might like to replicate or understand in a modeling framework. Then I'll describe the second part, a paper I published last year in Biophysical Economics and Resource Quality about looking at the structure of the US economy as related to the power consumption and the cost of food and energy as a core input. So, of course, a lot of this is motivated by thinking that a lot of normal economic explanations of concepts of secular stagnation coming back now after the financial crisis seem to be lacking a bit in some things. They discuss various issues such as population growth and demographics, which are important, debt issues. Sometimes they don't describe money in an endogenous way as how it might be getting created in a modern economy today. Explanations are of education. Maybe people aren't smart enough to invent the new technologies, and people don't have enough money for wages to pay for goods and services. So how do we fit all these concepts together? Usually there's not a lot of discussion about the fundamental role of resources, energy and food particularly, how this has changed over a long period of time, the difference between gross energy and net energy, which Jim described a little bit in his presentation, and technological characteristics of energy technologies, perhaps in general, at least efficiency of conversion of energy to end-use services. So I'm going to touch on some of these ideas. They kind of start from almost, we might say, a basic assumption of, do you think the Earth is finite matters? Most people think the Earth is finite, and then there's a camp that says, well, it's finite, but it doesn't matter, so I'm not going to think about it, which means it's not in your conceptual framework. Or there's a group that thinks, well, I think that's probably a relevant thing, and let me put it in my conceptual and or mathematical framework to think about it. So the Limits to Growth book, originally in the 1970s, represented here on the left, and then sort of neoclassical economics, or the Bottomless Well book, represented on the right, that says, yeah, the Earth's finite, but I don't think it matters because of substitution effects and things of this nature. So a characteristic quote of the Earth is finite, but it doesn't matter sense might be from Morris Edelman. There is no such thing per se as an exhaustible natural resource, such as a fixed stock of oil. The total mineral in the Earth is an irrelevant, non-binding constraint. Whatever is left in the ground is unknown, probably unknowable, but surely unimportant, a geological fact of no economic interest. So yes, I know the Earth's finite. Yes, I know there's a finite amount of oil or any other particular resource, but you know what? It doesn't matter because I don't make decisions based upon the total amount out there. I make decisions based upon whether I can economically extract a resource that I've found at the moment. The other perspective would be sort of the limits to growth perspective, that global ecological constraints relative to resource use and emissions, meaning sources or sinks, constraints in sources or sinks, would have significant influence on global developments in the 21st century. And humanity might have to divert much capital and manpower to battle these constraints, possibly so much that the average quality of life would decline sometime during the 21st century, right? So one side says, I think resource constraints are important, and I think it's going to have an impact on social outcomes. One aspect says, I don't think resource constraints are relevant, therefore, in some sense, I don't have to think much about social outcomes. So, have energy or resource abundance and constraints had significant influence on the structure of, I'll say, the post-World War II economy, and thus what are the social implications? So I'll look at some data for the United States and analyze that for the rest, a couple data points for the UK, United States, and the world, and then analyze some structural analysis of the United States. So some of this can stem from an anthropological perspective. So Joseph Tainter has what he calls the energy complexity spiral, that the energy resources going into a society are linked with its quote-unquote complexity. So his quote here characterizes it, most of the time complexity increases to solve problems. So this is to say I have some social problem or I have to battle my neighbors. You have some issue that a society or economy wants to face, and if it's an additional complexity on top of what they're already addressing, they need more resources to basically organize themselves and develop new capabilities.
Are these two things different or the same?
The two slides are the same.
Oh, okay, so I don't have to be going back and forth between them.
So he goes further to say that societies subsequently must produce more energy and other resources to pay for the increased complexity, right? So you want more complexity, you want more capabilities, you need more resources to do that. So a physical interpretation of societal capability. He goes further to say that the idea of energy gain, or what we might call net energy, which is how much energy is left over after you've used energy in the process of obtaining energy. In an agrarian society, this would be mostly food and biomass. So energy gain has implications beyond mere accounting. It fundamentally influences the structure and organization of living systems, including human society. So I'm going to sort of put this to the test for the modern economy, or at least the modern US economy, at the last part of this talk. One way to think about net energy, at least in economic terms, is how much money is spent on food and energy resources. So in this particular graph here goes from the year 1300 to 2008. These are data by Roger Fouquet at London School of Economics. But plotted in this manner, it shows how much money was spent on fuels to obtain energy services in England and the UK from pre-industrial and agrarian times to roughly today. The takeaway from this graph is that energy is expensive before 1800 and gets cheaper once the Industrial Revolution starts with the use of coal and the invention of steam engines. It drops tremendously after that point. So essentially, energy was more constraining and relatively expensive, represented here by a higher share or a higher cost of energy divided by the GDP. So what's shown here is the spending on all fuels divided by the GDP of England and UK at the time. So 30 to 40% pre-industrial, and then after that it declines to less than 10% by the time you get to World War II. Put on top of this, you can think of other aspects that you might use to characterize the state of an economy or the state of society, in this case population pressure. So this is taken from Peter Turchin's book, Secular Cycles. Population pressure here is the population divided by the population that can be fed on the land of England and UK, and you can see it goes through a sort of up and down cycle during this time, which is part of the point of Turchin's book, is that societies experience multi-century growth cycles, right? So there's this sort of ups and downs of society rise and fall over time, and these go through particular stages of societal capability, and that these are related to physical things like population and the resource base at which the population depends. So in this particular case, there's a cycle that lasts about 250 years, the time of the War of the Roses in England, at which the population is essentially near its minimum in the late 1400s, and then rises and falls over the course of 250 years. And during this time, they went through various times of equality and inequality and other kinds of social descriptions of the cycle. If we add on top of this food costs and not just think about energy costs, so the service of power in the blue is essentially biomass to feed animals to do work on the farm. People were also the prime movers consuming food to do work on the farm as well. So if we estimate their cost as an energy and food cost overall, then the dramatic decline in energy and food costs due to industrialization looks even more dramatic, right? It goes from 60% or more in agrarian times to, again, near 10% for modern times. So a model or a thinking of economic growth or thinking of the evolution of the economy over a long period of time essentially needs to be able to replicate something as dramatic as this pattern after 1800 to have a feel for the state of affairs today. So that's the longest time period history I know of to look at. Shorter time series starting in 1929 is just from Standard Bureau of Economic Analysis data in the United States. The green line at the bottom is what they characterize as consumer spending on energy goods and services divided by GDP. The red line is the spending on food and food services divided by US GDP, and then the white line is both of those added together. So the point here again is that energy and food is a basic cost to the economy measured in this way, declined since basically the midpoint of the Great Depression all the way until around 2002, and then they've been roughly flat since then. They went up during the commodity boom up until the financial crisis, and then today, or 2016 or 2015, roughly maybe near the point that they were in 2002. But these costs are no longer declining. The other dashed line here with the circles is the same type of data. It's the spending, the intermediate purchases by the food and energy sectors of the US economy divided by GDP, and I'll use that later as an indicator for net energy of the economy, at least as a proxy for net energy of the economy. So in the UK case, the lowest point of food and energy costs was the mid-2000s. The United States case, the low point in food and energy costs, basically for all time in the historical record, is around 2002. Doing this calculation for the world, but not having data as going as far back as the US or the UK, the answer appears to be the same. Again, two estimates of energy costs in green, one estimate of food costs, production costs from the Food and Agricultural Organization in red, and then adding those together for the white to be food and energy costs. The low point again seems to be around the year 2000, with the rise again with the price of oil mostly after that point, or at least the rise and decline with the price of oil after that. So we can ask ourselves again, all right, so have this change in food and energy costs, at which food and energy costs seem to have been declining with industrialization, certainly with the rise in resources costs due to oil in the 1970s, but then they declined afterwards again. But leading until 2002, in which the mid-2000s, or around the year 2000, seems to be the lowest food and energy costs in the history of mankind, or at least on the record. So in looking at this and the implications of distribution of money within the United States economy, I'm going to summarize some findings from this paper from last year in the Biophysical Economics and Resource Quality Journal, which looks at energy consumption rate of the U.S., energy and food costs in the U.S., and then what I'll show you here is my measure of structure, if you will, of the U.S. economy. So to do this, I use information theory to characterize the distribution of transactions. But so what is information theory? Information content is essentially predicated on the probability of an event occurring, right? What's the probability of something occurring? You can then calculate its information content. The point to take away from here is that less probable events, if they occur, provide more information. Highly probable events, if they occur, don't provide much information. So if I say, how's it going today? And you told me, or what's going on today? And you said, well, the sun rose today. I would say, well, that's great. The sun has risen every day that I've been alive. You haven't really informed me of much, right? Sun rises every day. It's highly probable. There's not a lot of information with that. Information entropy is the average information content of all the set of events that can happen. So instead of just looking at one event and saying what's its information content, information entropy averages all the things that can possibly happen and then creates a single number for the entire suite of events. So it's a systemic measure of distribution within the entire set of options you're looking at, whatever you're looking at. So what I'm looking at is the economic input-output tables of the Bureau of Economic Analysis, which the benchmark tables from 1947 to 2012. So these are my events, right? So I'm looking at the distribution of money in these economic input-output tables to see if the economy has become more complex or less complex, if you will, using a suite of indicators. So the probabilities of things occurring are the sectoral transactions as a fraction of all intermediate transactions. So if 5% of all spending was the oil and gas sector purchasing materials, goods and services from itself, then it would have a 5% chance of occurring, and that would be the probability. And then I would calculate information content of that and do this for every single transaction that's in the tables. So I'll look at three different metrics of information theory to describe the input-output table. So the first one is called information entropy. So just think about this. The larger the number is, in some sense, the more complex, if you will, is the economy. The less information is gained on average whenever you reveal any given transaction is occurring. And the more equally valuable is every single transaction. So if information entropy is increasing, each one of the transactions is looking more similar to all the others. They're all starting to look more similar. Similar but slightly different is what I'll call redundancy. This specifically describes the individual transactions in the economy. So if you have 100% redundancy, it means that every single transaction in the economy from one sector to another is exactly the same. And so that's 100% redundancy. If there's only one transaction in the economy, then this is 0% redundancy, right? In some sense, redundancy is having backstop options for economic transactions, having all sectors be equally valuable to the economy. That's a very redundant economy. This is based upon network science and network theory, which from a physical network standpoint, if you have multiple pathways to flow, say, electricity through an electric grid, then you are a more resilient or more redundant electric grid, because if one power line goes down, you have the capability of flowing power through alternate power lines to reach the same endpoints. So the more pathways you have, the more redundant. The more equal the pathways are, also the more redundant. Equality describes the sectors themselves. So this is slightly different than redundancy, but they're both measures of increasing distribution of money in the economy. So equality says, well, if I sum the total transactions going through every economic sector, if they're all exactly the same, then my economy in this sense, or this network, is 100% equal. This means that every transaction from one sector to another doesn't have to be the same, but the sum of all transactions to any given sector would be the same. This would be 100% equality.
One question, a transaction, is that a monetary transaction?
This is just, yeah, this is, I'm looking at just the money in the input-output tables. The concept is generic in the sense that it could be applied to any network that has a flow of any given thing going through it. Water, money, information, bits. So the concept is generic, but here, just applying it to the I/O tables. Okay, so now I'm going to look at the results here on this results table here. So I'm only looking at equality and redundancy. On the left-hand side is these calculations over time from 1947 to 2012. So each circle represents one of the benchmark table years. And then on the right side is the same calculations of equality and redundancy. I'll say here the numbers go from 0 to 1. So 1 is the maximum number. But on the right side, I'm plotting what I'm calling the net power ratio, which is my net energy metric. So the higher the net power ratio, the cheaper energy and food are in the economy. So this net power ratio is essentially the food and energy purchases by the intermediate sectors in the economy that are associated with food and energy divided by GDP, but then inverting that gives me a common net energy metric that people would look at, such as energy return on investment or these kinds of ratios. So the higher the ratio, the cheaper food and energy are. So there are essentially three phases of structural change in the US economy that I'll highlight. So the first phase goes from 1947 to 1967. During this time, the gross power, the increase in power consumption in the United States was going up at about 4% a year. So every year there was about 4% more power consumption in the United States. The net power ratio was going up at a higher rate, almost 3% a year, meaning that food and energy costs were getting cheaper at a high rate. Information entropy was increasing, equality was increasing, and redundancy was increasing. So basically, given all three of these metrics to look at what's going on, all three are showing that the economy is getting more quote-unquote complex, meaning that the money distributed throughout the economy is getting more equally distributed on all metrics. Then there is a second phase from 1967 to 2002 in which gross power consumption is increasing now, but at a slower rate. Net power ratio is increasing also, but at a slower rate than it was before. Information entropy is now declining or nearly stagnant. Equality is now declining and redundancy is increasing. So now 2 out of 3 metrics of increasing distribution of money throughout the economy are decreasing, and only one of them is increasing. So this is the main indicator for that there was a change between phase 1 and phase 2, is looking at the changes in sign of these information theory metrics. And then finally, phase 3, the change here is all numbers on the right-hand side table are negative. Gross power consumption is roughly flat during this time. We're roughly consuming the same amount of gross power today as we did in the early 2000s. The net power ratio was declining, meaning 2002 was the point of lowest energy and food costs in US history. And so going up to 2002, energy and food costs increased. So the net power ratio decreased. And now all three metrics, information entropy, equality, and redundancy, are all decreasing, meaning that money is now getting concentrated into certain sectoral transactions, and it's also getting more concentrated into certain sectors overall. So what are the takeaways from this? So there's 2 takeaways. Takeaway 1, energy and food have stopped getting cheaper since the 2000s. This is a change since basically the dawn of industrialization. This is a major discontinuity in the industrial age, and something that needs to be thought of in terms of what is the distribution of resources or money, and how is it affected by this change. This occurred about 10 years before the record high debt levels that reached over 300% of gross world product, and about 40 years after the initial oil crises, or the oil crises of the 1970s. Takeaway 2 is that these guys telling us that resources and complexity or resources and the distribution of money or resources in the economy are probably right. They're probably along the right in the correct lines of thinking, that the increased distribution of the flow of money within the US economy is connected to both increasing energy consumption in a gross sense and decreasing natural resource costs, in my case looking at energy and food costs. So if you want to read more, you can look up my paper on the details on this. So that's the end of my talk, so thank you very much, and it'll be up to Jem whether we take questions now or later.
Hey, Carey, is there any, you mentioned in the earlier session about the source of revenue, wage versus profit revenue. Do they have any implications? I mean, you're just talking money expenditure generally speaking.
Yeah.
The question that I have is, what about the functional?
So I'll just say one thing, that if you plot energy consumption, just US, energy consumption per person and wage share, standard data. Wage share starts declining in the 1970s, roughly, and then starts declining. Energy consumption per person stopped increasing in 73 with the oil embargo, and then was roughly flat and declining the last 10 years after that. The hypothesis would be that there's a connection between increasing energy resource consumption growing faster than population and being able to maintain a constant wage share. But if not, then maybe that was one realization that happened was, well, resources become constrained to some degree, so let's pay people less as a way to deal with that.